Class 10, welcome to physics class. In today's class we will try to see the image formation by convex mirror. In the previous class we have done the rules for drawing ray diagrams and the image formation by concave mirrors, uses of concave mirror, all those things we have discussed. And for today we will have to see image formation by convex mirror. Now for this formation of the image we require at least two reflected rays, two reflected rays, so as to intersect them, and at the point of intersection image will be formed. Got it? So for this convex mirror, instead of taking those objects at different positions, we can consider, or we can learn image formation by convex mirror by considering only two positions, one at the infinity and another in front of the mirror at a finite distance. So if you look, these two can be combined in one. If the object is placed wherever the position of the object in front of the mirror, the image will be always what? Virtual, erect and diminished. So let's see. And these are the positions of those what? Spherical mirrors. And these are the two positions that we are going to discuss, one at infinite distance in front of the mirror and another at infinity. When the object is at infinity, then all the light rays coming from the object incident onto the mirror can be treated as parallel to what? Parallel to the principal axis. And we know that for a convex mirror, when a light ray coming parallel to the principal axis, the reflected ray seems to be coming out from focus. So this light incident and reflected back. This reflected light seems to be coming out from focus. This incident light reflected along the same line again, because it is going to pass through the center of curvature, so it will be reflected along the same path but in the opposite direction. This reflected light seems to be coming out from the focus again. This also same thing, seems to be coming out from the focus. So all these virtual reflected rays intersect here at the point what we call as principal focus. So the image of the object placed at infinity, what happened? The image will be formed at focus, and it will be the size of what? Point. That means this is virtual. If it is virtual, the nature will be what? Always erect. So the image is what? Virtual, erect and highly diminished, very small, just like the size of the point. And when the object is placed in front of the mirror at finite distance, what happened? One light ray parallel to the principal axis after incident onto the mirror, the reflected ray seems to be coming out from focus like this, right? Yes. Another ray which is supposed to pass through the center of curvature will have to reflect back along the same path but in the opposite direction, right? As we have said here. Why? Because this is going to pass through the center of curvature. This is also same thing. It is going to pass through the center of curvature. So the reflected ray, what happened? It will go along the same path but in the opposite direction. So these reflected rays seems to be coming out again from where? From the center of curvature. So these two virtual reflected light intersect here at the point A prime. So your A prime and B prime will be the image for this object AB. Got it? Yes. In this case also, even though the object is placed at a finite distance, when you compare the size of the object AB and the size of the image A prime B prime image size is very small than that of the size of the object. So, and also erect. This upper portion is here also upper portion, the lower portion here lower portion. So we call it such type as what? Erect. Had this object at the upper portion, and in its image, if it is inverted, and this at the lower side, if it is coming upward, then we can say it is inverted. Got it? But here it is what? Erect. So these are virtual reflected rays. Intersection of virtual reflected rays will make what? Image virtual. So the nature of the image will be what? Virtual, what? Erect and diminished. Even if your object is brought closer and closer, so much close that it touches this mirror somewhere here, Okay, the nature of the image will be always what? It will be virtual, erect, and it will be diminished. Let's see, let me draw the diagram. Okay, suppose if the image object is brought somewhere here close, so much close that it touches the mirror. Got it? Let's take it that this is the object AB. Suppose if you bring this AB somewhere here, so what happens, this light ray which goes parallel to the principal axis, it will be reflected back like this. So this ray will be there. Got it? This is a real reflected ray. Somewhere here it is the virtual reflected ray. Got it? Another light ray which is supposed to pass through the center of curvature somewhere here like this. Got it? Let me draw like this. I can't draw that dotted line, it will be difficult. So when a light ray after incident like this, which is supposed to pass through the center of curvature, this reflected light will be reflected back like this, right? In this direction, right? No? So what happened? The two virtual reflected ray intersect somewhere here. So your image will be formed here. So this will be what? A prime, B prime, and this is the object AB. So even if you make the object touch with the spherical convex mirror, the image will be always smaller than the object. So what happened, at every position, at any position in front of the mirror, the image will be what? Always virtual, erect, and diminished. So instead of taking these two, we can also have only one. What we can say is that we can only say that wherever at the position of the object, the image will be always the image formed by the spherical convex mirror will be always virtual, erect, and diminished. Okay, let's see in the form of table. This is what you are going to see. Now this is the position of the object, position of the image, size of the image, nature of the image. So at infinity, we know that it is formed at the focus, okay, behind the mirror, that also, and it is highly diminished. It is of just like a point. So we call it as point size, and the nature will be virtual and erect. And if it is between the pole of the mirror and infinity, that means at infinite distance, image will be formed between P and F behind the mirror. It will be diminished, smaller in size. Diminished means nature will be virtual and erect. Now let's see the uses of convex mirror. Convex mirror can be used for rear viewing mirror of the vehicle. It may be in the motorbike, it may be in the light vehicles like Marutis, and it may be also in the heavy vehicles also. So all those rear means behind, okay, rear viewing mirrors which are placed on the side of the vehicle, they are all convex mirror. Why convex mirror are used? Why not concave mirror? Concave mirror cannot be used. Why? Because concave mirror, the nature of the image form is different. Okay, when the object is very far away, what happened? The image formed by the concave mirror is real, and at the same time it is also inverted. Got it? And smaller in size. So it will be very difficult to watch the inverted vehicles coming from the behind, right? So we will not use that type of concave mirror. And if it is used by concave mirror, when the one vehicle from your behind your vehicle, if it is approaching toward you, then what happened? At first, at very far away distance, the image of the other vehicle will be inverted, and it will be coming toward you, when the size of the image will keep on increasing, and at somewhere, what happened, the size of the image will be very big, and it will be inverted again, as if that erect one. Okay, so what happened, it will create confusion to the driver. So we will not use concave mirror, rather we will have to use convex mirror. And the more important thing why we use rear viewing mirror as convex mirror, here what happened, in the case of convex mirror, the image form is always virtual, erect, and diminished, right? And this rear viewing mirror, your spherical convex mirror, can accommodate a wider field of view. That is very important. Okay, so what happened, it can accommodate a larger area or larger space of the area of behind your vehicle. Okay, the larger area of the traffic can be seen through that what spherical mirror. And the second important thing is that it can be used also in blind corners. Got it? Blind corner means those crossroads from one side of the from one part of the road. If you can't see the traffic of the another road which is coming toward that crossroad, then what happen? We call it those roads as what blind corners. Okay, in the corner itself, at the corner itself, I mean. So just to make visible the traffic on the other road, okay, from our from the side of our rod, we have to place one what this spherical what convex mirror of larger aperture, so as enable to see the traffic coming from the other road. So let's see the picture of that what blind corner blind spot mirrors. Okay, these are the what convex mirror of larger aperture. Okay, from this side you are coming, so you just to see the other side on the road. We can't see any man standing here, but this man is standing on the other side. Okay, other road I should say, which cannot be seen from this side. When you approaching from this side, you can't see the another what side or a traffic on the other road. So if you place like this, you can easily see. So these are what blind spot mirrors. These blind spot mirrors are nothing but these are what spherical what convex mirror of larger aperture, right? Let's go back to that slide again. Yes, here. Now let's see the next the sign convention that we are going to use in the case of reflection by spherical mirrors. Okay, by convention means accepted by all over the world. Okay, we call it that as convention. And sign means what? For taking that object distance, what sign should be assigned to it, whether it will be plus or minus. So we call it those assignment, the accepted sign, we call it as what? Sign convention. So let's see. While dealing with the reflection of light by spherical mirrors, a new set of sign convention is used called the new sign convention, or it is also known as Cartesian sign convention. You must be knowing how to draw a graph by plotting those coordinates along two what mutually perpendicular axis known as Cartesian axis, x-axis, y-axis intersecting at the origin, right? So that it is similar to that one. Okay, now by convention we generally place what mirror or lenses on the right hand side and the object on the left hand side, so that what happen, the incident ray from the object onto the mirror or onto the lens will be from left to right. Got it? Let's see. The convention are as follows, right? The object is always placed at the left of the mirror. In the case of lens, it will be lens. Okay, we will not do it again in the case of lens. This will be for also for the lens. So the object is always placed on the left of the mirror or lens. This implies that the light from the object falls on the mirror from left to right hand side. Okay, all distance parallel to the principal axis are measured from the pole of the mirror. This is very important. Okay, this zero of every measurement should be on the pole of the mirror. In the case of lens, we call it as optical center, right? Yes, all those measurement, okay, in the direction of incident ray are taken as positive, while against it are taken as negative. Got it? If the measurement of the distance is in the direction of the incident ray, then that measurement will have to be taken as what? Positive. If the measurement is done against the incident ray, then it will be taken as negative. All measurement perpendicular to the principal axis and above the principal axis are taken as positive, while that below what? The principal axis are taken as negative. So let's see, and let me explain you by seeing this what diagram. Okay, so this is the spherical mirror. Either it may be concave or it may be also convex, no doubt. Got it? What happened? if the mirror is placed on this right hand side, object should be placed on the left hand side. This is the left hand side and this side is the right hand side. So mirror will be placed, either it may be what, concave or convex, doesn't matter. Okay, the mirror will be placed on the right hand side and the object will be placed on the left hand side, right? So the incident ray will be from this object toward the mirror. That means it is from left to right. So this is the direction of the incident ray. And for the measurement parallel to the principal axis, it should be measured from the pole of the mirror, right? So if you are going to measure, suppose image is from somewhere here and you want to find the distance of this image, then you have to start measuring from the pole along this side. So these measurement should be done, it should be done in the direction of the incident ray. So these measurement will be taken as what, positive. And if you are going to measure the distance of this object, for example, then you have to start it from the pole, 0, 1, 2, 3, 4, like that, so on. Suppose if it is 6 centimeter, then this measurement is done against the direction of the incident ray. Incident ray direction is from left to right, and your measurement is from right to left, right? So you have to assign that measurement as what, negative, right? The measurement of the distance or height above the principal axis that are taken as positive, that perpendicular we have to take it downward the principal axis, then we have to take it as negative. Got it? Clear? Yes, this is a thing that we have done, we have said just now, right? Yes. And now let's see the mirror formula. What is meant by mirror formula? You know, object distance, image distance, and focal length. What is the object distance? Distance between the object and the pole of the mirror, we call it as object distance. Got it? Distance between the object and the pole of the mirror, we call it as what? Object distance. Distance between the image and the pole, we call it as image distance. Distance between the pole and the principal focus, we call it as focal length. So the relation or the formula connecting these three what, physical quantity, okay, these three, u, v and f. U means what? Object distance. V means what? Image distance. F means what? Focal length. So the relation, okay, or the relation or the equation relating this object distance, image distance and focal length, we call it as what? Mirror formula. And the formula is what? 1 by v plus 1 by u is equal to 1 by f. In the case of lens also, lens formula will be there, and that lens formula, in that case this should be minus, okay, mind you. But in the case of mirror, what happened? This will be all plus. 1 by v plus 1 by u is equal to 1 by f. This formula is valid for all situations of all spherical mirrors, for all positions of the object, okay? Yes, we have used the new Cartesian sign convention while substituting numeric values for u, v, f and r in mirror formula for solving problems. Okay, for solving problems, what happened? You need to assign those new Cartesian sign convention to these image distance, object distance, focal length, radius of curvature. Okay, your radius of curvature r is equal to 2 times of focal length, small f, right? Yes. Now before going this one, let me tell you why this sign convention, I forget to tell you why this sign convention is known as what? New sign convention as Cartesian sign convention. It is just like that of the graph. Okay, graph, while you are drawing graph, you take it somewhere here, the y-axis, x-axis intersecting at this point known as origin, and this origin, from this origin you are going to take the measurement along x-axis, y-axis, like that. No, this is positive x-axis, positive y-axis, this side will be negative y-axis, this side is also negative x-axis. So it is similar to that one. If you are going to measure this length, then it will be taken as negative. If you are going to on this side, then x is positive. If you are going downward the measurement y, then this side is negative. If you are going to measure this height, that means this is along positive y. Okay, it is just similar to like this in the Cartesian axis while drawing graph. So taking the similarity, the analogy of this, we call it this sign convention as what? New Cartesian sign convention. Got it? Yes. Let's see in the case of what this magnification. What is magnification? Magnification is nothing but it is a comparison. Comparison of what and what? Comparison of the image with that of the object. Got it? So we can say comparison of a similar quantity, we call it as ratio, right? Ratio means what? Division of two similar quantities. So I will not read all those things, but you try to if you want to read it, you can pause it and you can read those texts written here. Okay, so as not to take much time of your valuable time, let me skip this part and let's directly go to that magnification. Magnification can be defined as a ratio of what? Image distance to the object distance. Image will be always first in the numerator, okay, and the object will come in the denominator. Okay, yes, it may be defined as what? The image distance to the object distance, and also it can be defined as the size of the image to the size of the object. Size means it may be, here it may mean also height. Got it? Size and height, they are taking with the same meaning. Got it? So it is expressed as a ratio of height of the image to the height of the object, or in some textbook you may find as size of the image to the size of the object. Got it? It can be also expressed as the image distance to the object distance, right? Let's see. Magnification is denoted by m, and if the size of the image is denoted by h prime, size or a height or size of the object by h, then it will be equal to what? M magnification is equal to height of the image to the height of the object. It can be also used in terms of what? The distance, image distance to the object distance. Here it is given here, magnification is equal to what? Height of the image to the height of the object. It can be also what? Defined as a ratio of minus of image distance to the object distance. I told you that image will be always in the numerator. Height of the image, distance of the image. Height of the object, distance of the object. Okay, but this should be of same quantity. If you are taking height of the image here and if you are taking object distance here, then it will be wrong. Then it will not be called as ratio. Got it? This is height. Comparison of similar quantity, we call it as ratio. Distance, image distance to the object distance. Height of the image to the height of the object. But mind you, one minus sign should be there in the case of mirror for these image distance to the object distance, but not in the height or size ratio. Got it? So what happened in the case of lens, it will be similar like this, but no minus sign there in the case of lens. But in the case of mirror, what happened? The magnification will be what? Minus of image distance to the object distance, or it may be expressed as height of the image to the height of the object. Now it is to be noted that the height of the object is taken to be positive as the object is usually placed above the principal axis. The height of the image should be taken as positive, okay, for virtual images, and as negative for real images. Got it? For height of the image should be taken as positive for virtual image. Virtual image means erect. Okay, real means what? It will be inverted, that means below the principal axis, and so it will have to be taken as what? Negative. And actually there are some signs to be noted. Okay, you may note down it. Okay, I'm not giving here, but let me do it here. Let's take this as blank space. Now if the magnification, okay, if the magnification small m, whether it will be visible or not, I have doubt that it can't view it nicely. Or yes, it may be also. Let's see. If the magnification, okay, if the magnification m, this one, if the magnification m is equal to coming out to be what? Negative, then what does this magnification negative mean? If this m is coming out to be positive, okay, then what does it signify? Now let me tell you, when magnification m is coming out to be negative, it means what? Your image is what? Real. Got it? If it is real, then what happened? The image will be erect or virtual? Erect or inverted? Yes, the image will be what? Inverted. And if magnification is coming out to be positive, then it will be what? Virtual. Got it? It will be virtual. Got it? As I'm writing with the mouse, it is very difficult for it just to write that like that over pen, so the handwriting becomes like this. So if you just know it, then it's okay, right? So if magnification is coming out to be negative, then it is what? Real. If the magnification is coming out to be positive, then it means the image is virtual. Now what about the numeral value? Suppose if magnification is coming out to be -1, -0.5, -3 like that. So that minus for sign, I have already told you, for that numeral value, let's see again. If the magnification m, okay, if this magnification m is less than 1, if magnification m is less than 1, then it indicates that the image size is what? Diminish. Got it? Diminish means what? Smaller in size. Diminish. And if the magnification m is coming out to be 1, that means it is same size. Got it? Same size, that means size of the image will be same as that of the what? Object. Got it? And if m is coming out its numerical value greater than 1, that means it represents what? Enlarged. That means the size of the what? Image will be more than that of the what? Object. Got it? So try to remember this thing. This is very important, okay? And this will be utilized again in the case of lens also. Suppose if your m, after calculation, if it comes out to be, say suppose -1, it means that minus represents what? Real. So the image is what? Real. If it is real, it will be inverted. 1 represents what? The size of the image will be as the size of the object, same as the size of the object, I mean. And if it is coming out to be, say suppose -2, for example, -2, that means minus represents real, 2 represents what? Enlarged. Got it? And if m comes out to be, say suppose plus 0.5 like this, 0.5 plus means what? Virtual. 0.5 means it is less than 1, so it will be what? Virtual, erect and diminish. Got it? So let's stop it here for today, and tomorrow we will do the next one, which will be what? For the lenses, refraction and all. Let's try to see in that area. Okay.